What if I told you that the absolute greatest threat to our modern infrastructure isn't earthquakes, it's not hurricanes, and it's not even heavy physical loads? No, it's something completely invisible to the naked eye. We're talking about a silent, multi-billion-dollar disease that is relentlessly attacking our global infrastructure, literally every single second of the day.
Welcome to this explainer. I am so thrilled you're here today because, well, we are going full laboratory mode. We're channeling the rigorous spirit of a master scientist. Let's call it the Dr. Chem approach, right? We're going to break down the complete experimental journey of corrosion and rust prevention. We'll be looking at the basic theory, the precise materials, chemicals, the exact experimental procedures, the calculations, and ultimately, the real-world applications that actually keep our bridges standing and our ships sailing. Okay, let's just dive right into this.
So, here's our roadmap for today. First, the threat of corrosion. Second, testing the breaking point. Third, calculating metal loss. Fourth, traditional defense mechanisms. Fifth, cathodic protection explained. And finally, number 6, the future, self-healing polymers. All right, kicking things off with Section 1, the threat of corrosion. To actually solve this problem, we first need to understand exactly what we're fighting at a chemical level. Basically, corrosion is an irreversible degradation of materials, but I really want you to think of it as much more than just, that ugly, flaky rust you see on an old car. It's an active, ongoing electrochemical attack. When we're talking about highway structures, pipelines, and aircraft, corrosion compromises their structural integrity. It creates severe risks to human safety and causes indirect economic consequences that are frankly staggering. So to fight it, researchers have to recreate this exact threat in a highly controlled laboratory environment. Which brings us to Section 2, testing the breaking point. So, to understand how resilient metals fail, the Federal Highway Administration, the FHWA, conducted these really fascinating exploratory tests to evaluate what's called stress corrosion cracking, or SCC. They used very specific U-bend specimens made from various grades of stainless steels, like 316LN and duplex grades. By physically bending the steel into this tight U shape and bolting it down, it perfectly simulates the intense, constant mechanical stress that our real-world infrastructure faces every single day. Now let's look at the meticulous procedure used in these experiments. It is all about total control. Step 1. The steel is polished with 400 grit sandpaper, just to eliminate any tiny machine marks. Step 2. The surface is thoroughly degreased using acetone, which is totally chemically inert to the steel. Step 3. A highly aggressive, high pH salt droplet is applied directly to the stressed curve of the metal. And finally, the researchers tightly control the temperature and humidity. The whole goal here is to create an evaporative condition where that salt deposit maintains a saturated liquid right on the steel surface. It's a perfect storm. And the outcome is incredible to look at under a microscope. Take a calcium chloride droplet on that 316LN stainless steel, for example. You'll notice that the corrosion occurs right near the center of the droplet. Why? Well, because the oxygen supply is limited there, so it forms the anode. Meanwhile, the outer rim, which is exposed to the air, becomes the cathode. You are literally looking at the exact moment localized pitting and rust begin to form beneath a single drop of liquid. It's like a miniature, self-contained destruction engine. But here's the thing, not all environments, or salts for that matter, are created equal. When researchers tested different salt solutions at 50 degrees Celsius, that's about 122 degrees Fahrenheit, they monitored the deliquescence point. That's just a fancy term for the relative humidity required for the salt to actually absorb moisture and become a dangerous liquid. Sodium chloride? It needed 75% humidity. But calcium chloride? Man, it only needed 30% relative humidity to stay active. Based on the observation of the metal samples, calcium chloride was the absolute most aggressive pit former. This kind of data tells engineers exactly what environments are the most hostile to our infrastructure. Moving right along to Section 3, calculating metal loss. Enter the weight loss, or W, method. I know, it sounds simple, but the execution is incredibly precise. Here's how it works. You take a pre-treated metal specimen, you wash it with double distilled water, dry it, and then weigh it on a scale with a sensitivity of plus or minus 0.01 milligrams. Insanely precise, right? You then submerge it in a corrosive solution for a set time, pull it out, clean it, and weigh it all over again. This method allows scientists to put a hard, quantifiable number on exactly how fast the metal is being eaten away. Once you have those weights, that's when the real analysis begins.
Researchers use these numbers to calculate the corrosion rate. But even more importantly, if they're testing a chemical inhibitor, something designed to actually stop the rust, they calculate the surface coverage and the inhibition efficiency. For example, in one particular study, by adding just 400 milligrams per liter of an organic inhibitor to a highly acidic environment, researchers were able to prove an 89.5% inhibition efficiency. These calculations are absolutely crucial because they're the ultimate proof of whether a defense mechanism is actually working.
All right, Section 4, Traditional Defense Mechanisms. So how do we currently fight back? Well, industry typically relies on 5 major prevention methods. First up, barrier coatings, like paint or plastic. They're cheap, sure, but they chip easily, need constant reapplication, and often contain hazardous volatile organic compounds, or VOCs. Second is hot dip galvanization, which literally bonds a layer of zinc to the steel. It's a great method, but you can't exactly do it on site, and the zinc does eventually wear away over time. Third, you could just use alloyed steel, like the stainless steel from our U-bend experiment earlier, but honestly, that's incredibly expensive. Fourth is cathodic protection, which we're going to look at in just a second. And fifth, modern hybrid solutions, like ion coat, which actually alloy the metal surface while providing a layer of inhibitors entirely without toxic chemicals. Pretty cool stuff. Now let's dive into Section 5, Cathodic Protection Explained. I love this part because cathodic protection is basically fighting chemistry with chemistry. It works by forcing the active sites on a metal structure to become passive. And how do we do that? By feeding them electrons. You can do this in 2 ways. The first is with sacrificial anodes. You literally attach a more active metal, like zinc or magnesium, directly to your steel pipeline. The corrosive environment attacks the zinc instead of the steel. It sacrifices itself as a decoy. It's wild. The second method is impressed current, which uses an actual external electrical power source to pump those protective electrons into the structure. It's highly effective, though, of course, anodes do eventually get used up and need replacing. And finally, Section 6, the future, self-healing polymers. This is where things get a little sci-fi. Using cutting-edge nanotechnology, scientists are now embedding microscopic inhibitor-filled capsules directly into protective paints and polymers. We are talking about hollow glass microspheres or lipid bilayer liposomes, which function just like the cells in your own body, and they are completely filled with healing agents. When the coating is scratched or damaged, these little capsules break open and release the inhibitor to autonomously fix the flaw. No human intervention needed. And it builds into something even more astonishing: stimuli-responsive chemistry. Some of these smart polymers don't even need to be physically broken to release their payload. They actually respond to changes in the environment itself, like a spike in temperature or a drop in pH caused by corrosive ions. A great example of this is the Diels-Alder reaction. It allows the polymer to form reversible crosslinks. If the material is damaged, an environmental trigger causes the molecular bonds to autonomously relink and heal, completely sealing the barrier back up without anyone lifting a finger. And that brings us to a rather breathtaking conclusion. Think about it. We've gone from watching a tiny drop of salt water aggressively eat through steel under a microscope, all the way to engineering intelligent, responsive molecules that heal our infrastructure the exact same way human skin heals a paper cut. With these smart polymers entering the aerospace, marine, and automotive industries, it really begs the ultimate question: will the rust of the past finally stay in the past? It is an absolutely incredible time for engineering. Thank you so much for joining me on this explainer. I hope you found this deep dive as absolutely fascinating as I did.